Hello everyone. Our project is Solar Eclipse Photograph Rotation. First, let's talk about a solar eclipse megamovie. Our client wants to make a set of solar eclipse images taken from 2017 from a variety of photographers across the US and align them to the same orientation so we can view the changes in the corona around the solar eclipse when we overlay those images together, kind of like this image right here, where we can see the corona features. So, our task was to create a CNN or regression model that can take a solar eclipse image like the ones below and rotate them to be solar north. Solar north, for simplicity, is just a common alignment position that we want all of our images to be.
The images we were given were very large, and the resolution varied from sizes that were greater than 4000 by 4000. This would make processing them be very time consuming. So to fix that, we resize all the images to 500 by 500 while maintaining the general aspect ratio. A lot of the images in the set had a significant amount of noise in the background. To clean out the noise, we used a process of median filtering. This created a 3x3 neighborhood that compared each selected pixel to the 8 immediately surrounding it and changed that pixel to the median of those values. This got rid of a lot of the noise. When we resized the image and maintained the aspect ratio, we did it so that the images wouldn't get warped, but it caused them to not be exactly 500 by 500. We remedied this issue by adding a black padding to the side of each image to make them exactly 500 by 500. We lessened the effect that the background had on each image of the eclipse by changing the dynamic range so that any pixel value who's had an RGB value of less than 128 would be completely set to 0 and turn completely black. This made it so that only the eclipse would appear in the image and no background would affect how the model processed it.
Hi, my name is Marcus, and I was tasked with creating a simple regression model to act as a baseline to compare against a more complicated CNN model. Now, I tested various regression models, but in the end, I settled with the XGBoost regression model because it gave me the best results. Now, in order to use any regression model, I had to first find a way to get values from the image to be used as the input to that model. And to do that, I used the SIFT, or Scale Invariant Feature Transformation feature extractor. And the way this worked is it would pull out a number of key points, like these circles here that are plotted here, and would assign them values, which would be plotted into a histogram, like this example histogram, which would then be piped into the image to be used as inputs. Now, this model was never super accurate. The best I ever got was an RMSE of about 8.3, and this was likely due to the complexity of the problem versus the simplicity of the model. The other thing that came up, though, was some issues with the integrity of the data, and we'll talk about that a little later. But for now, I will give it over to Brayan to talk about the actual CNN model that we worked on.
To begin, we need to group our images by the photographer's ID. This step is crucial because if we simply perform a standard train test split, the model could end up learning the characteristics of a specific photographer rather than general patterns in the data. To address this, I added a new column to our dataset to store each photographer's unique ID for grouping purposes. Another challenge is that our labels are angles, represented as floating point numbers, which aren't ideal for classification tasks. To handle this, I split the angles into 360 bins, effectively converting each degree into a discrete category. Now I initialize stratified group K fold. What's great about stratified group K fold is that it splits the data into groups, in this case by the photographer ID, while also maintaining the class distribution across the folds. This means that even if one photographer has significantly more images than the other, the percentage of samples for each class remains consistent within each fold. To compile the model, I used mean absolute error as the loss function. This metric evaluates how many degrees off my predictions are from the actual angles in the validation set. Finally, we move on to training the model. First, we use the .split function from stratified group K-fold to split the data into training and validation sets based on the data frame, labels, and groups. Next, the images are pre-processed by resizing them to 256 by 256 pixels to ensure consistency. With the data prepared, we build the model, train it, and record the validation loss and the mean absolute error for each fold. These results are then printed and appended to track performance across the different splits.
Unfortunately, Despite our best efforts, none of our models that we used came up with very good results. We found ourselves stumped until we made a crucial realization when looking closer at our data. We were under the assumption that our data was correctly labeled. However, this turned out to not be the case for a large chunk of our data. In this example, you can clearly see that with two very similar images from two different photographers, the two images do not match when looking at their features. In order to fix this issue, it will likely take many hours of sifting through our dataset and manually fixing these discrepancies, or getting specific metadata to help us generate the correct labels for our given dataset. So, despite our unfortunate discovery, there is still hope that we can potentially make a model that is able to predict the correct angle of rotation, provided we can get or make a dataset that is correctly labeled.